Today we are going to take up the chapter on simple machines. Let's consider the basic introduction. When we consider simple machines, what exactly is a simple machine? Why is it that a simple machine is required in our day-to-day life? What is the role that is played by a simple machine in our day-to-day life? Which are the devices that we categorize under simple machine? To make it simple, a simple machine is a device that is simple in its construction. Say for example a lever. A lever is nothing but an elongated rod which is fixed to a point that is free to rotate. This definitely is used to lift heavier loads by applying a small amount of force. So with the application of a particular force in a particular direction at a particular point, we get the convenience in doing work. Similarly, for example, a pulley also. When we have to draw water from the well, we see that we use a pulley at a convenient direction such that we get a convenient effort applied. So when we talk about simple machines, we definitely have to go with certain prerequisites to be known as far as this part is concerned. In prerequisites, we have what is force, what is the component of force, and why is it that force is required to be applied on a particular object so as to displace it. So these particular prerequisites will enable us to find this particular chapter simpler. Talking about certain definitions that are there in this particular chapter. First one we consider is load. We define load as the resistive force to be overcome by an external agency is called as load. It is denoted by the letter capital L and SI unit is Newton. The second term that we utilize here is effort. Now when we are applying load, definitely certain external agency is to be applied so as to overcome the load. So that external agency that is applied to a machine to overcome the resistive force is called as effort. It is denoted by the letter capital E, SI unit is Newton. As far as load and effort is concerned, these are two individual quantities when applied on the machine. We can determine how much advantageous the machine is in terms of force. And that's how we come to the third part, that is mechanical advantage. So we define mechanical advantage as the ratio of resistive force to be overcome to the external agency applied to overcome the resistive force is called as mechanical advantage. Mathematically, mechanical advantage is equal to load upon effort. It being a pure ratio is a unitless quantity. Then we come down to velocity ratio. The term is indicative of what exactly it stands for. The ratio of velocities. In this case, we have two forces that are accounting for the velocity. One is the velocity of effort and the other is velocity of load. We say velocity is nothing but rate of change of displacement with respect to time. So I define the velocity ratio as the ratio of velocity of effort to the velocity of load. But since, as I said, velocity is nothing but displacement of effort divided by time upon displacement of load divided by time. Since both these times are common, because both the displacements are traversed in the same time interval. So we see that the time factor cancels. As a result, we are left out with displacement of effort upon displacement of load. So velocity ratio is also called as displacement ratio. Again, it being a pure ratio is a unitless quantity. Next one what we consider here is efficiency. How efficient a machine is. Why is it that I'm utilizing a particular machine? Why is it that I'm using a particular machine? If it is not efficient enough, I need not use it. So we definitely use the efficiency as the ratio of work output to work input, or the power output to power input, or it can also be said as, since we are defining it as work output upon work input, we know work is nothing but load multiplied by displacement of load. Similarly, work input is nothing but effort multiplied by displacement of effort. So if I segregate it into two fractions, I get load upon effort multiplied by displacement of load upon displacement of effort. Multiplication is reverse division. So I can reconvert this equation as efficiency is equal to load upon effort divided by displacement of effort upon displacement of load. What is load upon effort? Mechanical advantage. What is displacement of effort upon displacement of load? Velocity ratio. So we get the relation between mechanical advantage, velocity ratio and efficiency as efficiency is equal to mechanical advantage upon velocity ratio. We say that an ideal machine is 100% efficient. But in day-to-day life, we have so many things in practice because we see that there is frictional resistance. We have to lift the machine part while doing certain amount of work. Now, all these factors and parameters account for the efficiency being falling down to less than 100%. So we say in an actual machine or in a practical machine, we say that the efficiency is less than 100%. We have a principle of machine which governs this law. The principle of machine says work output is equal to work input plus the work done in overcoming friction plus the work done in lifting the machine parts. With this basic fundamental definitions as far as simple machines are concerned, let's go to the law of moments, which you have studied in your 9th standard. Definitely, law of moments was about turning forces. So when a beam is held across a fixed point, that is called as a pivot, a fulcrum or a hinge, and you apply force on the body, then this body tends to rotate. The rotational effect of a force is called as moment of a force. And we define moment of force as the product of the magnitude of force multiplied by the perpendicular distance between the point of application force and the fulcrum. So if I calculate the anti-clockwise moments and clockwise moments, we say for the law of moments as for a beam to be in equilibrium, the total clockwise moments is equal to total anti-clockwise moments about the same fulcrum. I consider the first type of machine here, that is levers. We have seen in our day-to-day life how different levers are playing a vital role. Say, for example, a nutcracker. All of you must have seen your grandparents cracking the nut with the instrument or a device called a nutcracker. What exactly is a nutcracker? We have the fulcrum at the end, the load is a nut, and the part where we are applying the effort becomes the effort end. So it acts as a lever of class 2. Similarly, if you have been to certain construction sites, we see that people carry the load, the huge pebbles and rocks for building industries. Now these rocks are carried in a particular carriage which is called as a wheelbarrow. This wheelbarrow also acts as a lever. Okay, why consider these examples of wheelbarrow or maybe a nutcracker? We can go to our day-to-day example. We definitely cut our nails. The device that we use for cutting our nails is a nail cutter. Can you imagine that that is a form of a lever? Definitely it's a form of lever because you have load at one end, that is your nails. You're applying an effort at the other end. So you are getting a convenience in applying the effort. It is a lever of class 1. Similarly, we use scissors while cutting a paper. Definitely that also is a lever of class 1. During your kinder ages, you must have gone to a garden to sit on a seesaw. What is a seesaw? A seesaw also is a lever of class 1. So we see that wherever and whenever we see a particular device, it ought to be a machine. Machines do play a vital role in our day-to-day life. We eat, we talk, we drink, we sleep. Each and every function that we do in our day-to-day life involves a machine. Maybe simple or maybe a complex machine. But machine is a part and parcel of your life. However, as I said, we are considering the first type of machine over here as a lever. We define lever as a horizontal rod that is fixed about a point, free to rotate. That fixed point is called as the fulcrum or the pivot. And when we apply a particular load onto a particular bar, that part or that point at which the load acts is called as the load point, and the point at which the effort acts is called as the effort point. The perpendicular distance between the effort point and the fulcrum is called as the effort arm. The perpendicular distance between the load point and the fulcrum is called as the load arm. So if we apply the law of moments to levers, we have total clockwise moments is equal to total anti-clockwise moments. That is, load into load arm is equal to effort into effort arm about the same fulcrum. With this, we have certain amount of classifications of lever depending on the relative position of fulcrum with respect to the load and effort. We classify levers into 3 categories: class 1, class 2 and class 3. In class 1 levers, we have the fulcrum in between the load and effort. In class 2 levers, we have the load between the effort and the fulcrum. In class 3 levers, we have the effort in between the load and fulcrum. There is a small couplet which helps you to remember this. We can remember this particular classification of levers with the help of a small couplet. You know what a couplet is? It's 2 lines that are rhyming together with the last letters equivalent to each other. It says, FLE in the levers 3. FLE in the levers 3 may each in turn the centers be. FLE in the levers 3 may each in turn the centers be. That means in each category of levers, we have the load, the fulcrum and the effort being the centers of each other. So definitely we see that it is very easy to remember how we classify the levers. Now when we talk about the load, effort, fulcrum, definitely we are also considering the effort arm and the load arm. So when we say that the mechanical advantage is greater than 1, mechanical advantage is definitely load upon effort. But at the same time, it is also the effort arm upon the load arm. So when it is effort arm upon load arm and mechanical advantage giving you the gain in force, we say greater the effort arm distance, more is the mechanical advantage. So in which class of lever do we find that mechanical advantage will always be greater than 1? That means effort arm always greater than the load arm. The effort has to be at the extreme end, fulcrum at the other end. That means largest effort arm distance will be seen. So we have this in class 2 lever, like a nutcracker, lemon squeezer. All these examples you'll see fulcrum is at one end, effort is the other end, load is in between. So effort arm is maximum, load arm is less than the effort arm. So mechanical advantage always greater than 1 in class 2 lever. Mechanical advantage always less than 1. When do you have mechanical advantage less than 1? We have mechanical advantage less than 1 when the effort arm is less than the load arm. That means effort is between the load and fulcrum. Effort less than load and fulcrum categorizes into class 3. Like you have the sugar tongue, you have the fire tongues. In all these cases, we are applying the effort in between the fulcrum and load. So this type of lever will always have mechanical advantage less than 1. And in class 1 lever, it can take any combination of mechanical advantage as mechanical advantage equal to 1, mechanical advantage less than 1, mechanical advantage greater than 1. So we see here that classification of levers does enable us to find out whether a particular lever can be utilized in gaining force, gaining time, gain in efficiency, and so on.